Cause of thermal bridges. So what is causing a thermal bridge? It's a change of direction, or it's a change of material, or just a change of thickness. So all of them, they are causing thermal bridges, change of direction, change of material, and a change of direction, what is in a way a combination out of the two, like the direction is changing and the material is changing as well, like it changes from thermal insulation to air. Yeah, so it's a combination out of it, but I thought it's probably worthwhile mentioning that as well. So causes of thermal bridges, the causes are typically caused at window install edges. We're having our window glazing edges. We're having our roof ridge. We're having our eaves. We're having our intersection ceiling levels. We have our roof wall connections. There are wall floor connections. All of them, they're causing thermal bridges. The change of direction is causing a thermal bridge because our exposure, so if you're now looking at this corner, and we're looking now at our heat exposure here that is internally, like our internal exposure to the internal condition. And now we're looking at the external condition. So this little area is now fighting this big area. And this is the reason why we're having this temperature differences, because the area that are fighting with each other are differently big. And that's the reason we're having these curves. And this is the reason we're having thermal bridges. Does that make sense, guys? Can you follow? Yeah, all good. Cause of change of material, composition of the material is as well causing a thermal bridge. Difference of conductivity of the material, we're having as well a thermal bridge. And a good indicator of thermal bridges is our lines. So if these lines are parallel to each other, like these colored lines are parallel to each other, then we have no thermal bridge. Soon they start to have a curve, then we're having a thermal bridge. And then as well, these gradient lines that we're seeing here, this is now where the energy is going. Yeah, so these lines, when they are starting to bend, then we're seeing as well intensity of the thermal bridge and as well the width of that gaps that are showing us as well the thermal bridge. So if they're really close together, that means there's far more energy flow. If they're wide apart of each other, then there's less energy flow. If they're starting to bend, then we know that the thermal bridge has already an impact. So we see now this slab in here has an impact to here, to here, to here, to here, here, like we're still having here a little bit of bend, here a little bit of bend, here it's probably starting to be straight. And the same we're having down here, probably down the last line might be straight. Yeah, so we see that this thermal bridge has an impact over that whole height, pretty much. This is the reason why you normally, when you do a thermal bridge modeling, like we're not going to the depths normally in this course, you're normally putting 1.5 meters on both sides of the thermal bridge to see the full impact of that thermal bridge. Yeah, so we can't just say, cut it here, cut it here. There's still an impact of the thermal bridge. And if you want to know the full impact, you need to have uninterrupted buildups on both sides of that thermal bridge. There, when we have a change of thickness, then obviously the U value is changing and it has as well an impact. And we're seeing again how there are curves, how that is bent. And yeah, we see how they are closer together here, but over here, then they're similar. Like they're wider away here where the thermal insulation is better. And then they're becoming closer to each other. But you see how really they are close together here in that corner. That's where the thermal bridge is the biggest.